This is sections 10.1 and 10.2 of Honors Algebra 2, rational and real exponents. So we know how to deal with some exponents. We know what 5 squared is. We know that's 25. So we can take a number to an integer power. As long as that integer is positive, it's pretty easy. We can take 5 to the negative 2 power. So if our integer is negative, we can still do it. We know a negative exponent means we put it on the bottom as a positive exponent. That's 1 over 5 squared. That's 1 over 25. Easy. We can also do 0. 0 is an integer, so we should be able to do that. Well, 5 to the 0 power is 1. Anything to the 0 power is 1. So we can take a number to an integer exponent, an integer power. Well, there are numbers that are not integers, so what about 5 to the 1/2 power? Or even, dare say, 5 to the pi power. Well, let's think. If I take a number b and raise it to the 1/2 power, and then I square it, I know the laws of exponents, and those laws of exponents have to hold. They have to be consistent. So it has to work here. When I have a power raised to another power, I know I multiply the powers. So this would have to be b to the 1/2 times 2 power. Well, 1/2 times 2 is 1. So this would be b to the first power, which is just b. So since the square of b to the 1/2 is b, b to the 1/2 must be, and this is the way we define it, the square root of b. Because when I square it, I get b. So it must be the square root of b. So b to the 1/2 equals the square root of b. Interesting. How about b to the 1/3? Well, b to the 1/3 cubed, by the laws of exponents, I multiply those powers, and I get b to the first, which is b. So since the cube of b to the 1/3 is b, b to the 1/3 must be, and we define it to be, the cube root of b. Because when I cube it, I get b. Therefore, it is the cube root of b. So what about b to the 2/3? Well, by the laws of exponents, this is the same as b squared to the 1/3 power, right? Because 2 times 1/3 is 2/3. So this is the same then as the cube root of b squared, since the 1/3 power is a cube root. Well, b to the 2/3 is also the same as b to the 1/3 squared, because 1/3 times 2 is also 2/3. The order I multiply those exponents in doesn't matter because multiplication is commutative. So this would say the cube root, or this would say I take the cube root of b and then I square it. So these two things are equivalent to each other. The cube root of b squared and the cube root of b then squared. Pretty cool. So let's generalize this with the definition. If p and q are integers, with q greater than 0, because q is going to be the denominator of the fraction. If it were 0, we'd have a problem. And b is a positive real number, then b to the p over q power, so b to a power that is a fraction of p over q, is the qth root of b raised to the p power. So think of a fractional exponent as giving you a power over root. The top number, the numerator of the fraction in the exponent, is the power. The bottom number is the root. And remember, I can always write it in two ways. I can take the root first and then raise it to the power, or I can raise the number to the power and then take the root. So, some examples will make this clearer. 16 to the 3/4 power. Well, this would have to be the 4th root, because 4 is the denominator of the fraction in the exponent, the 4th root of 16 cubed. Now I could do 16 cubed and then take the 4th root. That would also work. But then I'm going to deal with a bigger number, 16 cubed, and having to take the 4th root of that. Whereas this will give me a smaller number. The 4th root of 16 is the number I raised to the 4th power in order to get 16. Well, that's 2. So this is 2 cubed. And 2 cubed is 8. 2 times 2 times 2. So 16 to the 3/4 power is 8. Number 2, 25 to the negative 3 halves power. Okay? Well, I know what to do with a negative exponent. It means I put it 1 over that to the positive exponent. Then I apply my fractional exponent definition, and I know that this is then the square root. So when it's the square root, I don't have to write the 2 in front of the root. Without a number there, it's assumed to be the square root. The square root of 25, then cubed. So the square root of 25 is 5. This is 1 over 5 cubed. 5 cubed is 125, so it's 1 over 125. Neat. Number 3, 9 to the 2.5 power. Well, that's a decimal. Well, all decimals that end can be written as fractions, so this is really 9 to the 5 halves power, right? 5 over 2 is 2.5. So this is the square root of 9 to the 5th power. Square root because 2 is the denominator. So this would be 3 to the 5th power, and 3 to the 5th power is 243. So 9 to the 2.5 power is 243. It's pretty cool. You can take a fractional exponent on an integer, and you get an integer. You get a whole number. Let's go backwards. Let's write this in exponential form. The cube root of a to the 5th, b to the 3rd over c squared. Okay, that means a cube root, we know, is the 1/3 power. So I'll take everything that's inside of the cube root, a to the 5th, b to the 3rd, over c squared. I'll raise the whole thing to the 1/3 power. That's what it means to take the cube root, is to take the 1/3 power. I can then take that 1/3 power, and I can apply it to everything on the inside because everything is multiplied and divided. Remember, if there's any addition and subtraction going on there, I cannot apply it. But I can if everything is multiplied and divided. So this is a to the 5th to the 1/3, b to the 3rd to the 1/3, over c squared to the 1/3. A to the 5th to the 1/3 is a to the 5/3 power. B to the 3rd to the 1/3 is b to the 3 times 1/3, which is 1, so b. And then c to the squared to the 1/3 is c to the 2/3 power. We'll stop there. Number 5. Write in exponential form and in simplest radical form. So I've got square root of 8 times the cube root of 4. Well, square root of 8, I know, is 8 to the 1/2 power. The cube root of 4 is 4 to the 1/3 power. Alright, well, I can only combine those if the bases are the same, and right now they're not the same. 8 and 4 are not the same numbers. But they happen to be numbers that have a common base. In other words, 2 to the 2nd power is 4, 2 to the 3rd power is 8. So I can replace it with 2 cubed. I've got 2 cubed to the 1/2. I can replace 4 with 2 squared. I'll have 2 squared to the 1/3. And then I just have a power raised to another power. I multiply the powers. I've got 2 to the 3 halves power times 2 to the 2/3 power. And now I've got the bases the same. And I can add the exponents. So that is 3 halves is really 9 over 6, and 2/3 is really 4 over 6. So now I've got a common denominator, and I've got 9 over 6 plus 4 over 6 is 13 over 6. Two to the 13 over 6 is my answer in exponential form. I was also tasked with writing it in simplest radical form. So let's take 2 to the 13 over 6, and let's realize that 13 over 6 is really 2 and 1/6. So this is really 2 squared times 2 to the 1/6. 2 squared is 4. 2 to the 1/6 is the 6th root of 2. So that is my answer in simplest radical form. So I can write it as a fractional exponent, or I can write it with a radical. Number 6. Let's solve this equation. X minus 1 to the 3/2 power equals 8. Well, how do I get rid of that 3/2 power so that I can get x by itself, which is what I need to do if I'm solving it for x? Well, to get rid of a 3/2 power, I'm going to raise both sides to the reciprocal power. I'm going to raise both sides to the 2/3 power. So I've got x to the minus 1 to the 3/2, and I will raise that whole thing to the 2/3 power. And I'll show you why. That will equal 8 to the 2/3 power. I can raise both sides to the same exponent, and that will not change my equation. It will just look different. So when I take the left-hand side to the 2/3 power, I've got a power raised to another power. 3/2 times 2/3 becomes 1. Hey, that's nice. So I've got x minus 1 to the first power, which is just x minus 1, equals 8 to the 2/3. Well, I know 8 to the 2/3 is the cube root of 8 and then squared, power over root. So x minus 1 is equal to, the cube root of 8 is 2. And then I've got 2 squared, and that's 4. So x minus 1 equals 4. That means x equals 5. Nifty. So my solution set is the set containing 5. Number 7, let's solve this one. 5 times x to the negative 1/3 power equals 20. Well, before I raise both sides to the negative 3 power in order to cancel out my power, I need to get the 5 on the other side, so that I just have what is raised to the exponent by itself. X to the negative 1/3 needs to be by itself with 20 divided by 5, or 4, on the right-hand side. Now, I can take both sides and raise it to the negative 3 power, the reciprocal of the power I've got. That way I'll have x to the first power, because negative 1/3 times negative 3 is positive 1, equals 4 to the negative 3rd, which is 1 over 4 to the positive 3rd. Well, what is 1 over 4 to the positive 3rd? Well, 4 to the 3rd is 64, so this is 1 over 64. So x equals 1 over 64. I've got the solution set as the set containing 1/64. Okay, Mr. Shaver, so what about 5 to the pi power? You promised us that. Well, we can do pretty well by approximating pi as a rational number, like a decimal that ends. So I could find 5 to the 3.14159 power. My calculator can do that for me. 5 to the 3.14159. I know I can do that because that can be written as a fraction, and I know how to do fractional exponents. So this is equal to about 156.9918748. So is that what 5 to the pi power is? No, not exactly, because pi is not exactly 3.14159. Pi goes on forever, never repeats, and never ends. It cannot be written as a fraction. But the best I can really do is to approximate it with a fractional exponent, or with a decimal that terminates, a decimal that ends, because that can be written as a fraction, and I know how to do that. Let's explore this further. Let's consider the equation y equals 2 to the x power. We can easily find several values of y for particular values of x. If I plug in negative 3 for x, for example, I have 2 to the negative 3rd power. That's 1 over 2 to the positive 3rd power. That's 1/8. That's 0.125. 2 to the negative 2 power is 1 over 2 squared, which is 1/4, which is 0.25. 2 to the negative 1 power is 1 over 2 to the first power, which is 1/2, and that's 0.5. I know how to do 2 to the negative 1/2 power now. That's going to be 1 over 2 to the 1/2. That's 1 over the square root of 2, which is about 0.7, not exactly, about 0.7. It's an irrational number. 2 to the 0 power, anything to the 0 power is just 1. 2 to the 1/2 power means the square root of 2, and that's about 1.4, again, not exact. 2 to the first power is 2. 2 to the 3/2 power is about 2.8. It's the square root of 2 cubed. And then 2 squared is 4. So I can find a whole bunch of values for this function, and I can graph them. I've plotted them right there. Those are those 10 points. It would be great if I could connect these as one smooth curve. To do so would require plotting a whole bunch more points. How many more? Infinitely many more. For what values of x? Well, for every single value of x that is there on the real number line. Well, that includes rational numbers, which I know how to do because I can do fractional exponents, and rational numbers can be written as fractions. That also includes irrational numbers for x. And the best I can do with those is to approximate them with rational numbers. So the whole graph of y equals 2 to the x does look like this, a smooth curve which has the x-axis as a horizontal asymptote. You'll see as x goes in the negative direction, it keeps getting closer and closer to the x-axis, but never quite gets there. And it keeps growing as x gets positive, greater and greater in the positive direction. So there must be some point associated with 2 to the radical 3 power, 2 to the square root of 3 power. Square root of 3, again, is an irrational number. There must be some point associated with it on this curve, because it is somewhere on the x-axis. But the best we can do is to approximate that point with closer and closer rational exponents. Fortunately, this can do it for us. So 2 to the radical 3 power, it tells me 3.321997085. Well, what it's doing is it is approximating it with rational numbers that are really, really close to radical 3. So what we've essentially done is established that it is theoretically possible to take irrational powers. So that means we can work with them. So let's simplify these expressions. Example number 8 is 6 to the radical 2 power over 6 to the negative radical 2 power. Well, bases are divided and they are the same. That means I subtract the powers. This is 6 to the radical 2 minus negative radical 2 power. Well, minus a negative becomes plus a positive, so that's 6 to the radical 2 plus radical 2 power. That's a 6 to the 2 radical 2 power, which, as you know, would be 6 squared to the radical 2 power, which would be 36 to the radical 2 power. Number 9. 4 to the pi times 2 to the 3 minus 2 pi. Well, I can only combine them if the bases are the same. So let's rewrite 4 as 2 squared. Then I'll have a common base of 2. 2 squared to the pi is 2 to the 2 pi power, power raised to a power, multiply the powers. And now I've got two things that are multiplied with the same base, and so I can add the exponents. This is 2 to the 2 pi plus 3 minus 2 pi power. Well, the 2 pi minus 2 pi becomes 0. This is just 2 to the 3rd power, which is just 8. So that whole expression I had before is just the regular ordinary number 8. That's pretty cool. Number 10, 3 to the 2 radical 2 power raised to the radical 2 power. Well, a power raised to another power means I multiply the powers. You know that by now, right? So that becomes 3 to the 2 times radical 2 times radical 2, or radical 2 times radical 2 is radical 4, which is 2. So that's 2 times 2, which is 4. So 3 to the 4th power. And as we all know, 3 to the 4th is 81. And then what's really cool is I can solve equations that involve variables in the exponent, like 8 to the x power equals 1/4. Well, 8 and 1/4 can both be written with 2 as a common base, because 8 is 2 cubed, so this is 2 cubed to the x power, and 1/4 is 2 to the negative 2 power. Think about it. So that means 2 cubed to the x is 2 to the 3x power. The bases are the same, I multiply the powers. So now I've got 2 to the 3x power equals 2 to the negative 2 power. That means if these two things are going to be equal, these two expressions are going to be equal, and they've got the same base, it must be that their exponents are equal. So 3x must equal negative 2, which means x must equal negative 2/3. And that is the solution to my equation. So that's pretty cool. If I can write both sides of my equation as the same number to a power, then I can set those powers equal to each other. Let's see another example, and we'll be done. 5 to the 4 minus x power equals 25 to the x minus 1 power. Well, I can write 25 with the base of 5 as 5 squared. So that's 5 squared to the x minus 1 power. Okay, well, 5 squared to the x minus 1 means I multiply the powers. That's 5 to the 2x minus 2. I'm making sure that I distribute the 2 into that whole expression. Now I've got the same base on both sides, so I take the exponent expressions and set those equal to each other. 4 minus x equals 2x minus 2. And I just solved that regular ordinary linear equation for x. So I'll add the 2 over here. That makes 6 minus x equals 2x. I'll add the x over there. That means 6 equals 3x. That means x equals 2. So the solution to my equation is the set containing 2. And I can always check my answer by plugging it in and making sure it works. So here are your immediate practice problems. On number 1 and number 2, I want you to simplify and show me all the steps you're doing in order to simplify it. On number 3, I want you to solve that equation. You've got 6 times x to the 2/3 power equals 54, so make sure you divide both sides by 6 first, and then raise both sides to the 3/2 power so that you eliminate your exponent of 2/3 on x. And that is the end of sections 10.1 and 10.2.